Okay, I guess it's about time to start. So let me share a screen with you first. Okay, I presume you can see my screen.
I can see your screen.
Okay, wonderful. Okay, I'm going to continue with antennas. Before we get started, let me ask if you have any questions regarding antennas. Okay, so I find this interesting plots on the internet. I just thought I would share that with you. So one of this is the simulation of electromagnetic wave leaking from a hole in the waveguide. One thing I'd like to tell you that is that let me see. This one looks like I lose my signal. Okay, so this is a simulation using a method called FDTD, which stands for finite difference time domain. Okay, this method is very powerful. You can solve Maxwell's equations quite easily. And many people have used this method to solve Maxwell's equations. So you can actually solve Maxwell's equations with pretty complicated geometry, like a waveguide with a hole. And here is just a point source in homogeneous medium. Okay, this was done with the software called MIP at MIT. The second one is probably done by a student in course ME 513 in the mechanical engineering department in Purdue. But what I want to notice, or want you to notice, is that when you look at the spherical wave, and when the wavelength is short, okay, but the wavelength gets shorter, the spherical wave becomes locally like a plane wave. If you just focus the attention around this part of the wave, it looks locally like a plane wave because the radius of curvature of the spherical wave is very large compared to the wavelength. Okay, and over here too, if you go far enough, you can see that you can make a local plane wave approximation. So this is the rationale for local plane wave approximation that we will use quite a bit in the far field. Okay, and so because of that, you can actually, as we said before, study the radiation pattern from an array of antennas. For this case, we put 5-element array here. I think we have 5 elements, or 4 actually, just 4 elements, I'm sorry. And then you can calculate the far field. The far field, as we showed last time, we started the far field with the radiation integral, which is this thing over here, which is something like JR prime. And then with the minus J beta dot R prime, okay, with a plus here actually. And then outside we have a spherical wave. Okay, so one of the key things that you should notice is that that factor here, which I call F beta, is the Fourier transform of the current that you have. So this Fourier transform relationship is very important. And if you master the insight of finding the relationship between Fourier transform and this factor and the current, you can actually easily figure out how an array pattern would look like. And we say that we did that for an array, and then we get something like sine nx over sine x kind of behavior. This is called a digital sink. Okay, a digital sink is rather complicated. Okay, let me see if I have an expression for it. The x for the digital sink turns out to be, for the simple case that we have in our lecture note, x is given to be something like beta d cosine phi plus psi. Okay, psi is the phase, the linear phase. And you assume that this is 1, and then the second one would be added with the phase, something like this, and then the third one will have this phase, and then the fourth one will be have this phase. Okay, phi is this angle. Phi is this angle in the cylindrical coordinate system. We are assuming that the observation point is in the xy plane, and then beta is 2 pi over lambda. And then d is the spacing between the array. Okay, this is d, and this is d. So you quite easily see that when you change phi, okay, when you change phi, x is going to change. But how can you make x change rapidly when you change phi? You can increase beta. Okay, when you increase beta, which is the frequency, okay, a little bit of change of the angle will give rise to a large change in x. And when x change very much, then this function would change. Okay, so you can get some kind of an insight, which is that if I make the frequency large, I'm going to get more and more lobes or side lobes. That means that as a function of phi, this function is going to vary rapidly, and you are going to have a lot of lobes, okay, rapid changes of the thing. And what are the other ways that you can make the x change rapidly as a function of phi? Phi is the observation angle, it's just moving around here. Okay, you can also make d larger. If you make d larger, it means that when you make the array spacing larger, you're going to see more and more lobes as you go around the antenna. These are called lobes. Okay, like the other place you can probably have seen the word lobes being used is in your brain. Your brain has a right lobe and a left lobe. I'm sorry. Okay, so you can actually change the phasing of this array, and depending on the phi that you picked, you can get the radiation pattern to look like this. And this is, as I said before, acts constructively in this direction. Okay, this is the broadside direction. So this second array that we have actually is called a broadside array. Broadside. Because it radiates predominantly in the broadside direction. This is called the end fire direction. This is called the broadside direction. But this antenna radiates in the broadside direction. It's called broadside array. You can get that effect by changing phi. And on the other hand, this is called an end fire array. Okay, so this pattern happens essentially due to the constructive and destructive interference. In certain direction, we have destructive interference. There's no power flowing that direction, but in certain direction, you have constructive interference. And it's all because of that, and it's all because of that function, okay? So we did this quite carefully. But I like to give you some insight where you can actually tell us how to calculate this integral very rapidly. Okay, let me rewrite this. This integral that we have would give me a spherical wave on the outside, and then an integral, and then something like this, okay? So this is just a Fourier transform integral, FT integral. And how do we gain quick insight as to how this integral should behave? So if I look at an antenna array, I can use something that I learned in digital signal processing. The current actually can be thought of as impulse functions at these locations. Okay, the current J are just set of, actually the currents are pointing in the Z direction, and then they are just impulse functions. Okay, and that we can get from, we can gain some insight from digital processing, digital signal processing. We can think of this function Jz as being equal to a pulse function. Okay, if I have this function, maybe let me call it a box function. Okay, if I take this box function, maybe can make it slightly big, slightly bigger, and then multiply with an infinite impulse train. Okay, multiply by infinite impulse train. An impulse train will look something like this, which is repeating itself. Go to infinity, and then here it repeats itself. This is an infinite impulse train. Okay, there's one thing that you should know very well in signal processing. If you do not know that knowledge, you should remember it now. What is the Fourier transform of an infinite impulse train? Infinite impulse train here means a train of impulses that repeat themselves. Okay, what is the Fourier transform of this? Does anybody know? Say if I have this function of x, okay, maybe I can just use lowercase f. What is the Fourier transform of this thing? Does anybody know? Anybody good in signal processing can tell me the answer right away.
Is it a sinc?
No, not a sinc. The Fourier transform of a box function is a sinc. Okay, if a Fourier transform this function, if a Fourier transform this function, okay, ft it, okay, then you get a sinc function. Think of kxa or something like this, okay? This is a Fourier space. A Fourier transform of a box function is a sinc function. Sinc function is just sine x over x. Okay? But what is the Fourier transform of an infinite impulse train? Anybody knows?
So when we start to widen that rectangular pulse to the infinity, the Fourier transform becomes it like starts shrinking to one like small pulse and becomes delta function, I guess.
Mm-hmm. And what else? I guess nobody knows. Nobody in the class knows what the Fourier transform of an infinite impulse train is. Okay, you have a train of impulses. The Fourier transform is also an infinite impulse train. So if you take this Fourier transform and ask yourself, what is f of kx? It is also a train of impulses. Okay, there's something you should know. You should memorize by heart and commit this to memory. Okay, so if this is spacing d, then you can show that this is 2 pi over d. 2 pi over d. Okay, if you don't know this fact, please remember this fact now. I find it very useful as an engineer. Okay, that the Fourier transform of an infinite impulse train is another infinite impulse train. You can prove this very easily, and I don't have the time to prove it. Okay, so this fact is very useful because it says that if I have a Fourier transform of this current, a finite train of impulses. Okay, if I only have, say, 5 sources. Okay, if I only 5 sources, what is the Fourier transform of this? And this can be written as being equal to, let me just say that this is equal to an infinite impulse train, okay, infinite impulse train, which is this one over here, multiplied by the box function. Agree? Okay. So this is in the x space, in the coordinate space. A finite array, a finite set of antenna array is the same as an infinite set of array antenna multiplied by a box function. Okay. What would be the Fourier transform of this then? The Fourier transform of this would be equal to the Fourier transform of this convolved with the Fourier transform of this. Okay, this Fourier transform to a sinc function, but this Fourier transform to another infinite impulse train, but with different spacing. Okay. Okay. So you can right away figure out what the Fourier transform of a finite impulse train is. With the convolution of this thing, okay, then it is what you have just found, that if you convolve these two together, you get a sinc, okay, and then a sinc that repeats itself, and then a sinc that repeats itself. You get a digital sinc. Okay, you get a digital sinc when you Fourier transform a finite set of sources. And then when you change the phases on this thing, you can just delay. You add them with a linear phase, the Fourier transform will be just shifted in the Fourier space. This is in the Kx space. Okay, this is in the Kx space. This is Kx. Okay, is this clear? You can easily figure out what the Fourier transform of a finite set of array is just by manipulating things around in your head. Okay, and that's why you have this aliasing things. If you have studied signal processing, you know how aliasing comes about, because you have to convolve this signal with a infinite impulse train again, which give rise to aliasing effects. Okay. So because of that, we can easily figure out that the sinc function should come about, and that's what you should have, okay? And if you don't have any question on this, I'd like to move on to ask the question as to why is far field valid? Okay, when is far field approximation valid? Okay, so when is our far field approximation valid? We say that we can use parallax argument and say that we can approximate this with r minus r hat dot r prime. Okay, if you have this r being here, r prime being here, this is r minus r prime, then this distance is r hat dot r prime. This distance is r hat dot r prime. And then you can use this parallax argument, but this approximation can also be gotten using algebra. So maybe I can show you the algebra method. So what you can show is that r minus r prime square, okay, is just r minus r prime times r minus r prime. And if I expand this out, I would get r dot r minus 2r prime dot r plus r prime square. Okay, and r dot r is just r square, and then I will have 2r prime dot r. Okay, and then the last one would be just r prime square. Okay, r prime dot r prime is r prime square, which is just r prime square. Okay, so I'm going to assume that r square is large. This is a plus sign, sorry. I'm going to assume that r prime is going to be much smaller than r. Okay, so if r prime is going to be much smaller than r, I can make an approximation to this thing. Okay, I can make an approximation to this thing and keep only the most important term. And the important thing to notice here is that I'm actually after this quantity. This quantity is actually equal to the square root of this quantity. Okay, that is equal to that. And I'm going to make an approximation that this is small. Both of these terms are small. Okay, those terms are small. I'm going to use Taylor series expansion to expand this function. When you have 1 plus x to the power of n, okay, we all know how to do that Taylor series expansion. It will be 1 plus nx plus n times n minus 1 over 2x squared plus something higher order term. And if you know how to do Taylor series expansion, you would know how to do that. So I can write this in this manner so that I take out the r square, and outside it will just become this. And then I will have minus 2r prime dot r over r square plus r prime square over r square half. Okay, I just have that. And these two are going to be small. Okay, these two are going to be small. Which of the two terms is smaller if you compare this term and that term? If r prime is small, which one is even smaller? Of the two, which one is smaller?
Should be the right-hand term.
Very good. The right-hand term consists of the square of a small number. Okay, very good. And then this term only has not the square of a small number. Who was the one who spoke just now, please?
Me, Ryan.
Okay, hi, thank you, Ryan. So this is even smaller. I'm going to do a Taylor series expansion by assuming that both of these two terms are small. Okay, so if I do that Taylor series expansion, I'm going to get that r minus r prime, okay, is going to be approximately equal to, keep this term over here and then do a Taylor series expansion of this. And if you don't mind me doing that quickly, it's just algebra, which I think you know how to do at home. Okay, so the first term is going to be this. I just keep the first term there. And I have to divide n is equal to half. Okay, n is taken to be half in this expansion. So this half makes the 2 go away. And then the second term that I should keep is r squared over 2r squared. Okay. And then I will have to keep the next term over, which is this term over here. Okay. If I were to keep this term over here, it will contain the square of the small number. The square of the small number. And furthermore, I have to divide by this prefactor. The prefactor would be half times minus half divided by 2. So it is going to be minus 1 over 8. Okay. So it is going to be pretty small. But what is important is that if I plug it in, I can ignore this term because this term is smaller, as Ryan said. Okay. So when I put in the other term in this series, I'm going to be only keeping this term when I square it. So the last term there would be something like maybe 1 over 8 r prime square over r square squared. Okay, it's going to be something like that. Okay, then if I look at this thing again, this term is going to be small. Okay, this term is going to be, sorry, is this r prime square? Let me see. Okay, so I have to ask the question as to when I can throw out these two terms. Okay, I can throw out these two terms because when I make this approximation, I'm only keeping the first two terms. If I keep only the first two terms, then it would be r minus r prime over r. And this would be the same as r minus r hat minus r prime, because r divided by r is equal to r hat, the unit vector. Okay, so if I kept only the first two terms of the series, I get back this approximation that I have obtained by the parallax method. So if I want to keep higher order terms, which means these two terms over here, I will make the approximation more accurate. The question to ask is, when can I throw out these terms? Okay, when can I throw out these terms? I need to go through the analysis, which I'm not going to go through in detail with you. The criterion would be that since if I do make this approximation, okay, I have to put it in the exponent. I will have to multiply by this thing because the approximation is actually made in the exponential part, which means that I'm actually going to and beta is not small. Okay, it's not necessarily small. It can be large. Then in order to be able to throw out these last two terms, the criterion would be that, let me see, the criterion that I have obtained is that beta r prime square over 2r is much, much less than 1. So if this criterion is satisfied, then they can throw out the last two terms. I don't have the time to go into the details with you, but that turns out to be the criterion. I'll write it out more carefully in the lecture notes as to how this comes about. Okay, so if this is satisfied, then the far field approximation is good. Okay, far field approximation is good. Okay, so what does this mean? It means that if r, the observation point, r is the distance between the observer and the source, is much, much larger than beta, beta over 2 r prime square, okay, r prime square. If this is true, then it says that this can be evaluated if beta is 2 pi over lambda. Then this says is that if r is much, much larger than pi over lambda, r prime square, then far field approximation is good. Okay, what does this mean? R prime is the location of the source. So if you have an antenna array, like what we have studied before, okay, we put the array on x-axis, and R prime goes from zero to maybe NB, the size of the array, okay? So if the size of the array is such that this quantity is small compared to the observation point, and if you put your observation point somewhere, say R, okay? And if the size of this array is small compared to the observation point, by this ratio, then you can make the far field approximation. And then when is this not valid? It is not valid if lambda is small. So it says that if lambda is small, R has to get bigger. That means that if the wavelength is very short, you have to go even further away in order to make the far field approximation, okay? And that distance is called the Rayleigh distance, the distance at which you can make so if you have a size of an array here, say if the array is of size W, your R has to be much, much larger than pi over lambda W square. And this is called the Rayleigh distance. Okay, this is called the Rayleigh distance. And that distance has to be larger, the higher the frequency. Okay, and the demarcation boundary between these two things. So you can say that if I have an antenna array, say, I put them over here, and in the beginning, this antenna is going to launch a wave like that. And if you go far enough, the wave is going to turn into a spherical wave. So because we say that if R is much, much larger than R prime, we have the far field approximation. And whenever we have the far field approximation, the wave becomes a spherical wave, as we show in the beginning, okay? The wave becomes a spherical wave, and we also show later on that the wave becomes a spherical wave if you're far enough, which means that if you have an array antenna, eventually the wave that leaves the antenna has to look like a spherical wave, okay? So you have a spherical wave here, okay? And that distance is called the Rayleigh distance. And this is called the far zone. Far zone. This is sometimes called the Fraunhofer zone in German. Fraunhofer zone. Okay. And this is called the Fresnel zone. Fresnel zone is the zone where the far field approximation is not valid. And then here's the near zone. So roughly when you have a set of sources, you have an array antenna. Okay, then the radiation field zone is divided into the near zone. In the near zone, you essentially have near field physics. You have quasi-static physics where static electromagnetic theory holds true. And then you have the Fresnel zone where it's the midway point between far zone and the near zone. Okay, so roughly these are the three zones. Are there any questions on this? Are there any questions? Yes.
I have a question. Why
Sure.
did not we consider distance d between elements in our derivation? Does it make
The
sense?
derivation of the Fraunhofer zone or the far zone, why the spacing between the element is not important? Is that
Yeah.
your question?
Why does the
Okay, it's a good question. Let me answer your question for you. So when we did the far field, okay, when we did the far field, we're actually comparing the magnitude of r and r prime. So like we go into this integral that we have to begin with. Okay, we begin with an integral. Let me write the integral here. We started out with this integral. Or we started out with this Green's function. Okay, we want to approximate this Green's function with this Green's function. Okay, and in order to make this approximation, we only have to compare two numbers. The two numbers that we have to compare, okay, let me see if we can put this somewhere, maybe here. The two numbers that we have to compare is the magnitude of r prime and r, okay, or r prime and r. We only have to compare these two numbers. And what decides r prime is not the spacing of the array, it's the total size of the array, okay? Spacing doesn't matter. Okay, spacing doesn't matter, it's the total size of this array that decides whether you're in the far field or not. Can you see that? R prime runs from this distance to that distance, and in order for you to make the far field approximation, you compare this distance with that distance over there. Okay, it doesn't matter how many antennas you put in this distance. It's this size, the size of the aperture that matters. Does this answer your question?
Yeah, I'm wondering if, say, r, distance between the point when where we measured the field and the distance between antennas are the same. Will this approximation be valid? It's yeah, it's not a real situation, but anyways.
Yeah, so in order to make this approximation, you only compare two numbers. You compare the numbers to decide when you can throw out these higher order terms, okay? You can throw out these higher order terms when they are small compared to this leading order term. You compare r prime and r, for instance, okay? In order to throw this out, you also can compare r prime and r when you throw this term out, okay? So actually I might have gotten this term wrong, okay? I will go and check, but it's done carefully in the lecture notes. I might have written this term down wrongly. Okay, this might be just r prime dot r because I have r prime dot r over here. Okay, so you compare only this term with that term, and hence you don't need to compare the other things. So essentially, you're comparing the size of the array with the distance to the observation point. The observation point is over here. Okay, you put your observation point over here. Okay, so the number of antennas you put in this antenna design is not important. It's the size of the array that is important. Okay, the size of the array is determined by ND, for instance. If the spacing between the antennas is d, if you have n of this antenna, the size of the array is n times d. Okay, does this make sense?
Yeah, that makes sense. Thank you.
Okay, good. Then I can move on then. If you understand this concept well, I'd like to actually go through different types of antenna very quickly with you. Okay, different kinds of antennas. I'm going to use mainly heuristics to go through this. I'm going to not talk about things rigorously. Let me spell heuristics carefully. Heuristics. Okay. And you have learned a lot of wave physics. You have learned a lot of EM physics too. Okay. You have studied, for instance, quasi-static physics. You study plane waves. And then you have studied transmission lines, which is a kind of another kind of wave. And then you study waveguides. Okay. And then you have studied resonators, which actually a kind of device used to trap electromagnetic energy. And then you study radiation from dipoles. So I feel that if you have all these things under your belt, you should be able to understand a lot of things approximately. Okay, we also have studied circuit theory, for instance. Okay, and then so if I give you an antenna design, which I can say looks something like this, driven by a voltage source, and then there will be current flowing on this antenna, and then it's going to give out electromagnetic radiation. You're going to use all these heuristics that you have learned to understand the radiation of this antenna. Okay, let's try to do that. Use heuristics. Okay, so let's start with the dipole antenna. This is a dipole antenna. The dipole antenna looks something like this. Is a piece of wire, okay? And then you drive it with a voltage source, maybe something over here. The current would flow like this. And the current on the antenna would flow. And if you were to plot the current distribution, it's going to look something like this because the current has to be zero at the two ends. Because the currents are zero at the two ends, the voltage has to be at the peak. So this very much behaves like a transmission line in the sense that if you look at transmission line, if you drive this with the voltage source, okay, the current is going to flow like this. The current is going to go to zero here, okay? And then the voltage is also going to peak at the open circuit at the end. So you can think of a dipole antenna as being a transmission line that is slowly being flared. Okay, I use the word flare. Open up the end, and if you open up the end, that current is going to still go like this, okay? And it's going to go to zero at the end. And finally, when it's completely flared like this, the current is going to look something like that. But you know that this thing will resonate at lambda over 4 that we have learned before. Okay, at lambda over 4, the current distribution will look something like this. The current is maximum and then go to zero there. Okay, so this open circuit transmission line would resonate at lambda over 4. Okay, so this dipole antenna would resonate at lambda over 2 because lambda over 4, when you open it up, it becomes a lambda over 2 size antenna. Okay, so you're going to see this kind of physics quite a bit, and you can actually show that a piece of wire is a waveguide. A piece of wire is a waveguide, and there's a mode in this waveguide called a Gumbau mode. Why is a piece of wire a waveguide? You can think of a coaxial cable first, okay? And you think of a coaxial cable first. The inner conductor is a waveguide, and the electric field will look something like this with the magnetic field going like that. And if you make this outer conductor further and further away, if you make the radius of the coaxial cable becoming bigger and bigger, then the coaxial cable becomes a wire. A wire can still carry a mode, and this is a picture of a Gubaud mode. Okay, a Gubaud mode, and you can have a current flowing this wire. The electric field will look something like this. The magnetic field will go something like this. Okay, and the only difference of this from a coaxial cable is that this thing radiates. Okay, this thing radiates and loses energy, whereas in the coaxial cable, there's no way for the energy to leak away. Okay, so this thing would radiate. I can think of this as a Gubaud line, if you want to think of it that way. You can see wave bouncing back and forth. And when you hit the resonance of this antenna, it resonates approximately when it reaches half a wavelength. Because this thing resonates at a quarter wavelength, this thing will also resonate at the quarter lambda over 2 because of that Gubaud mode that is propagating on this piece of wire. Okay, any questions on this? So when the antenna resonates, something called resonance tunneling happens. So when you hit the resonance of a structure, the current is going to be large. Okay, just like if you have an LC tank circuit, if you hit the resonance circuit, the resonance frequency of this LC tank circuit, the current is going to be very large. Okay, for the same reason, if you hit the resonance frequency of this dipole antenna, which happens around lambda over 2, the current that you can drive into this antenna becomes very large. I guess Hertz realized this many years ago, so he tried to make his antenna having 2 spheres. So when he drives the antenna, he drives it with the 2 spheres, and the 2 spheres act like capacitors. Okay, this is like capacitor, and this is like an inductor. Okay, so his 2 spheres with the wire of the antenna form a LC tank circuit that causes the Hertzian dipole to resonate at the much lower frequency. The next antenna I like to talk, are there any questions on the half-wave dipole? Okay, why does it resonate and why does it become efficient at half a wavelength? Okay, it becomes a very efficient radiator when you hit half wavelengths of the dipole.
About the dipole,
Yes.
do we have fringe capacitance and inductance at the end of wire?
Well, the fringe capacitance is very small because if you look at the electric field here, electric field is going to look like this, right? Right, if you have positive charges at this end and negative charges at this end, electric field is going to look like that, okay? And you can say that there is some kind of a capacitance between these 2 ends because the electric field is going to go from this end to that end. So there is some kind of a capacitance involved due to this fringing field. But since the fringing fields are so far apart, these charges are so far apart, that capacitance is very small. This is not like the transmission line where you have positive charges over here, negative charges over here. And then you drive it with the voltage source, the fringing field is going to be strong because the positive charges and the negative charges are very close to each other. Whereas for the case of a dipole antenna, they are very far apart. So the fringing field is going to be very weak. Okay, so it's not important, not as important as that in a transmission line or a microstrip line. Okay, does this answer your question?
I was wondering about that dipole with the 2 spheres at the ends, mostly.
Oh, there would be a capacitance here too, because if you think about this, if this is positive charge, this is negatively charged, there'll be fringing field. And this capacitance is bigger. And Hertz deliberately make it that way so that he get a bigger capacitance. And if he gets a bigger capacitance, then this can be approximately modeled as a inductor in series with a capacitance. okay? And this inductance can come from the wire here. And the capacitance can come from the two spheres. And the two spheres can have fringing fields interacting with each other. If you make the sphere bigger, this fringing field capacitance becomes bigger. And it has this LC tank circuit, essentially, that allows him to drive current into the Hertzian dipole that was very short. Okay? Does this answer your question?
Yeah, it answers it. Thank you.
Okay, good. So let's move on and look at this Yagi-Uda antenna. Yagi-Uda antenna is actually a very clever design. This is actually designed around 1926 by Professor Yagi and Professor Uda in Japan. Okay. At the time, they don't have supercomputers. Now we have numerical software. To simulate this. Okay. And this is called a folded dipole. A folded dipole is a way to make antenna to become smaller. Say if I have a non-folded dipole, this has to be lambda over 2 before you hit resonance. And hitting resonance is important because when you hit resonance, the current is large on the antenna, it radiates warp. So how can you make the antenna smaller? One way is to think of first a loop antenna. If you have a loop antenna, okay, if the current is going that way, or you can think of a shorted transmission line. Okay, so if you have this being lambda over, if this is a, say something like this, then if you have this open circuit, then this would resonate around lambda over 4. Okay, that's why you have lambda over 2. But if you make it short circuit, okay, then you can get this to resonate around a, I guess, lambda over 2. Okay, lambda over 2. And then you can actually make this thing smaller. Okay, you can make this thing smaller. And then this would be lambda over 2. But lambda over 2 would be over the larger length. Okay, so if you make this into a folded dipole, you can make this length to be lambda over 2. Okay, I think that's the argument. And maybe I say it wrong. Lambda over 4, lambda over 4. Let me see. If it's a short, sorry, if it's a short, okay, if you put a short there, it can still resonate at lambda over 4. Okay, so if you put a short here, it resonates like this, say the current is the maximum. Okay, we have studied the case of a shorted transmission line and an open circuit transmission line. Okay, so if it is a short circuit, you can still get it to resonate around lambda over 4, which means that if you can make this total length lambda over 4, it will still resonate. Which means that this thing can be lambda over 8. So you can make the dipole half as small by folding it so that it resonates at the longer wavelength, even though the dipole antenna is small. So this is just the physics of a folded dipole. Then the surprising thing about the Yagi-Uda antenna is that this array in the front act like a waveguide. Okay, they act like a waveguide, which is hard to prove. Okay, but it was found by Yagi and Uda that if you make this less than lambda over 2, okay, a half-wave dipole is lambda over 2, but if you make this length to be less than half a wavelength, they become like a waveguide, and this is called a reflector. Okay, it's larger than lambda over 2, and then it stops to be a waveguide. So these are also called directors, because eventually they would direct the energy forward and causes the energy to go in the direction and then to bounce back from this reflector. So we have a simulation of this. Like I asked my students to actually simulate this antenna using FDTD. Okay, you can see that the wave is being guided by the array, by this array or this array down here in the forward direction. But this reflector is actually bouncing the wave so that all the energy of this dipole, okay, the dipole antenna is actually being guided forward, okay? And then, of course, you have seen this picture before, and this is the case when the structure is much, much less than the wavelength, then you have to use circuit physics. And when the structure is much, much larger than the wavelength, like the prism here, you have to use ray physics. So optics becomes important, okay? So this is the Yagi-Uda antenna. And then we have another antenna that uses resonance tunneling. So resonance tunneling is a very important concept in antenna design. So you have a small dipole antenna that is not a very good radiator. However, if you put this antenna into a cavity and you pick the cavity size such that it resonates at the operating frequency, omega. Okay, so as you have played with the swing before, in a park when you were a little kid, if you know how to pump a swing, the swing would swing bigger and bigger, and you don't have to apply a lot of energy because you hit the resonance frequency of the swing. The same thing, this cavity has a resonance frequency. We studied cavity resonators before, okay, from our knowledge of cavity resonator. You're going to hit the resonance of this cavity, and then the field will be very strong inside. E and H will become very strong, okay, inside. And then there will be some fringing electric field, E field, at the slot of this antenna, okay? And the slot of this antenna would leak out the electromagnetic energy and causes it to leak. So this is called a slot antenna. Okay, and it can radiate very well because you hit the resonance frequency of this resonator. So it very much is the same principle that if you have an LC tank circuit, in order to get the current to be large, okay, you have to hit the resonance frequency of this LC tank circuit, then you get a huge current to flow through this LC tank circuit. And by the same token, if you hit the resonance frequency of this cavity, you get the electromagnetic field E and H to be very strong inside the cavity, and it will leak out a very strong energy outside, okay? And the same thing happens to a microstrip patch antenna. If you have a microstrip patch antenna, it looks something like this. And it's a resonance structure. This is the resonance structure. And it can be understood very easily because the antenna is like a patch with open circuit all around it, okay, all around it. So if you have an open circuit, then this antenna can be approximately modeled by an antenna that looks like this, a patch antenna, electrical patch, but with magnetic wall, okay? with PMC wall. I kind of discussed this with Ivan yesterday in the office hour. Okay, this is the PMC wall. So if you have a PMC wall, then by duality principle, n cross h has to be 0. So n cross h has to be 0 on this wall, which means that the electric field, no, the magnetic field has to look something like this. Okay, on the wall of this, the magnetic field has to look something like this. This is the H field. Inside the cavity has to look something like this. But n cross H is J. Okay, so if you look at the boundary condition on the PEC patch, so let's assume that this is a PEC patch. Okay, n cross H is equal to J. So if H looks something like this, J will have to look something like this. Okay, J will have to look something like this. And similarly, all the J's are tangential. So there's no normal component of the electric current on the patch H, which means that it behaves like an open circuit. The PMC wall is making it look like an open circuit. And then you can think of this as the first principle, think of this as the resonator due to that I have a transmission line. I have an open circuit at the two ends. Okay, we know that the voltage will go to maximum, the current will go to 0, the current will look like this. Okay, if you have open circuit, then the I look like this. And then the voltage has to be maximum at the two ends. Okay, when it resonates. So V looks something like this, I looks something like this. And then, so you can very easily figure out that this structure will resonate when you hit lambda over 2, okay, half a wavelength. So when L is half a wavelength, this structure will start to resonate. And when it starts to resonate, you can use resonance tunneling to enhance the current on the patch. And if you use resonance tunneling to enhance the current on the patch, then the current will start to radiate wow. Okay, that's how a microstrip patch antenna works. Very much like a cavity backslot antenna. But then L being lambda over 2 is not very good. And of course, you like to make this antenna as small as possible. One way to make it small is to have a antenna being fed like this. Then you're forcing the current to go through a tortuous path. I call it tortuous path. Okay, you're forcing the current to flow through a tortuous path. And then if this path is lambda over 2, then this structure would also resonate. And you can use resonance tunneling to get this antenna to radiate wow. Okay, any questions on microstrip patch? How it works? Okay. So the next thing is a horn antenna. Horn antenna is an antenna where you gradually go from a waveguide to free space. Okay, and you probably learned that most transmission lines have 50 ohms in the characteristic impedance, but free space, okay, free space have an impedance of 377 ohm. So if you think of a transmission line being terminated by free space, if this is 50 ohms, it wouldn't work. There would be mismatch. So what we do is that we learn something called a quarter wave transformer. Okay, so if you pick a quarter wave transformer, so what you have is Z naught, and then you have something called a ZT here, and then you have a Z load. Okay, what is the relationship between ZT, Z load, and Z naught, so that there's no reflection in this structure over here. Do you remember what ZT should be? It's one of the take-home exam problems.
It's ZL squared over Z naught squared, probably. I don't remember exactly, but something like that.
Okay, if you don't remember, anybody remembers? ZT is the geometrical mean between the load and the impedance of the other line. So it has to be some value in between. Okay, so if you have something like this is mismatch, so one way to do that is to actually to add a lot of transmission line sections of different impedance. Okay, it's hard to design an impedance that works like this. So if you have different sections of transmission line, you gradually go from Z naught to Z load. Okay, and this antennas kind of does that. It gradually transitions from the impedance of the waveguide to the impedance of the free space. The waveguide might have 50 ohms here. Okay, and the free space is 377 ohms. So you try to design the antenna in such a way that they are impedance matched, so that if you send a wave in here, most of the energy is being radiated and does not get reflected. So these are just different kinds of horn antennas. And of course, you can also design what is called a corrugated horn antenna. Does anybody remember why we need corrugation in this horn antenna? We discussed that once before in one of the lectures. Does anybody remember? It turns out that in the circular waveguide, there is a mode that is axially symmetric. Okay, if you have a circular waveguide, there's a mode where the electric field looks something like this. Okay, the E field looks something like this. That is the TE01 mode. And that mode is axially symmetric, and hence if you can exploit that mode, the radiation pattern that you get from this antenna is axially symmetric. And it will have a radiation pattern that looks like this. So in order to enhance the axially symmetric mode, you use corrugation. Of course, you can also use mode filters. Remember that? And this second horn antenna will give you a very nice axially symmetric radiation pattern. Okay. A Vivardi antenna is the same concept. Okay, it's actually invented by this guy Gibson. He admires the musician Vivardi a great deal, so he decided to name this antenna after him. And again, you can think of this as very much like a horn antenna. The impedance gradually changes from that of a low impedance value to a high impedance value, so that when you send in the wave from here, the wave can be matched to the impedance of free space, and then it will leave this antenna gradually. And it turns out that this antenna is designed to be broadband. When the frequency is high, it will leave the antenna very early. When the frequency is low, it will travel a longer distance before it leaves the antenna. So this antenna can operate over a broad bandwidth. Okay, this is the Vivardi antenna. And another way of making antenna is called a reflector antenna. This is a reflector antenna of the Cassegrain design. And these are called quasi-optical antenna. And you use ray theory to design them. Essentially, these antennas are so big, okay? L is much larger than lambda. So in that regime, you can say that electromagnetic wave behave almost like light ray. When the ray has very short wavelengths, they behave like rays. Okay, so if you shoot a electromagnetic energy out from this horn antenna over here, you will reach this secondary reflector, which is convex. You'll bounce the electromagnetic energy off and fill in the reflector antenna in that manner, and sends a beam that is collimated out, and that will give rise to a radiation of this antenna. The advantage of this is that it has very high directivity. We study the concept of directivity. Okay, this antenna will have very high directivity because we essentially focus the energy of the electromagnetic radiation forward. So it's very good for radio astronomy. When you want to pick up a very weak signal from the outer space, okay, when you want to pick up very weak signals from the outer space, you use the, let me see. Do I have this? Because, okay, let me see. The reflector antenna is very useful and it's very important in radio astronomy. It turns out that there are two big reflector antennas in the world. One is called FAST. It's actually in China, someplace in China. And the other one is Arecibo reflector antenna, okay, in Puerto Rico. This one is getting very old, as you can see. This is just newly built. Okay, this is in China. This is in Puerto, how do you spell Puerto Rico? Puerto, oops, why does it go that way? Puerto Rico. Okay. Puerto Rico, okay. And you can actually see a antenna feed. We can send out signal or receive signal being bounced off from the outer space. And this is good for something called the Seti Project. Seti Project is some thing for extraterrestrial intelligence. I don't know what S stands for now, but this is extraterrestrial intelligence. Okay, maybe this is, I don't remember what S stands for now. Maybe it stands for science. Okay. And you can also have what we call a reflector array. That is, you can put patches on the surface of a piece of plastic material, and by shining microwave on it, the wave will bounce off with different angles. Okay, so you might have a ray that goes like this, like this, like this, like this, and then all of them will bounce off the same angle. So they will be parallel after that. By adjusting the spacing of this array, you can get them to all bounce off in the same direction. And this is what this is actually. Okay. You can also make lens antenna, which are quasi-optical. These are also quasi-optical. You can think of this as being almost operating like a lens in optics. Okay, almost like a lens in optics. And then you can have things like something called a PFAR. PFAR is a planar inverted F antenna. If you look at this thing, it looks like an F. It is inverted, so they call this PFAR. The good thing about it is that this thing would resonate roughly when this is lambda over 4, okay, because it's an open circuit over here, a short circuit over here, this structure would resonate around lambda over 4, okay? So it is smaller than the other kinds of antennas, and then you can drive it with a voltage source, which is this location over here, and you can actually get this thing to be matched, impedance matched, depending on where you put the driving source, okay? So this is a very popular cell phone antenna because it's only a quarter wavelength long. And then you can also have what is called the U slot. The idea is very similar, that if you can control the current flow, if you can control the current flow on the patch antenna, you can control its resonant frequency. So you drive this antenna with the current source over here, the current will have to go like this, very much like a folded dipole. Okay, go like this. Instead of just going back and forth like the case of the patch antenna, you can get the resonance frequency to be lower because the current would have to be going over a longer path length. And you can look at this antenna from a different perspective. This is actually copper. This is copper. This is a dielectric sheet that separates the copper. And this is insulator. So the current will flow something like this, okay? And because of that, it has a lower resonance frequency. And this is something that I did in my research group many, many years ago. Let me see, I probably have to put this in display mode before the video will play. Let me see if it will play. What does it say? I probably have to do something. Can you see my screen?
Yeah, it's presentation mode. You probably push the escape button and you'll be back to it.
Okay. I guess, can you see the thing playing or you cannot see it playing?
I can see it. Yeah, it's supposed to be a video.
Okay, can you see it playing now?
Yes. No,
Okay, this is what we call an XM antenna on a car. It's used to talk to the satellite, and it was something done by my research group in 2005, some 15 years ago. Okay, so let me go and exit the presentation mode. Let me see how to exit it. End show. Okay, this would be that, and then of course you have seen this before when you have a Hertzian dipole. I guess this has to go into presentation mode as well. Okay, you can simulate this, and then you can see this kind of thing. And then another antenna that's very popular is called the RFID antenna, where you put this on a food package or a merchandise package, and you like to make this antenna as small as possible. The idea is the same. If you can control the current flow, make the current go in a tortuous path, you can make this antenna a lot shorter, and you can make it half its original size, okay? And this is something I did with some people at Hong Kong U, okay? And then the last antenna is actually a loop antenna. And it turns out that if you just design a loop antenna naively, it will start to resonate. It will start to resonate. But if you were to load the antennas with capacitance, then it starts to have a uniform current, and you can delay its resonance frequency, okay? So the reason is because if you just have a simple loop antenna, if you drive it with a source, and when this length is roughly lambda over 2, then this loop antenna will start to resonate. When it starts to resonate, it would have non-uniform current. And that's not good. If it's non-uniform current, it means that the field is non-uniform inside. Okay, and if non-uniform inside, it will not make a good reader. This is used for RFID reader. Okay. In order to read a lot of, say, test tubes simultaneously, if you're in a laboratory, you want to read the labels of all these test tubes simultaneously. You want the field to be uniform inside. And one way to make the field uniform is to load this with a capacitors. Okay. And then I have some students design something like this. This is the animation of that RFID reader. And you can actually get it to produce a uniform current around the loop without having to resonate. Okay. I guess I'll stop here since I run over time. Are there any questions before we stop? Any questions? If no questions, I guess I'll let you go. For tonight's office hour, Bo Yuan Zhang will give it at 8 p.m. tonight instead of the usual 3 p.m. Okay, since I'm rather busy today. Okay, thank you for coming. Unless you have any questions, I'll end the meeting.